Welcome, and thanks for being here. You can get comfortable. There's nothing you need to do right now. No need to focus too much. Just let the words be in the background. Some thoughts might catch your attention, others might drift away, and that's perfectly fine. If you enjoy this kind of calm space, you can leave a like to support the channel and subscribe if you'd like to come back again. It really helps, and it keeps this space going. For now, just take it easy. Let the sound settle, let the day fade a little, and allow yourself to rest. The idea of the universe slowly moving toward a state of maximum calm is based on a simple physical principle known as entropy, which describes the tendency for energy to spread out and become evenly distributed over time. And when this process is applied to the entire universe, it suggests a future where all large-scale activity gradually fades, not through a sudden collapse or dramatic event, but through an extended, almost imperceptible quieting of motion, structure, and usable energy. In the earliest stages of the universe, matter and energy were highly concentrated, and this concentration made change possible, allowing stars to ignite, galaxies to form, and complex structures to emerge. But as billions of years pass, energy continues to flow from regions of higher concentration to regions of lower concentration. And once this flow becomes nearly uniform everywhere, the processes that depend on energy differences begin to slow and eventually stop. This slow progression toward uniformity is what is commonly called the heat death of the universe, though the word heat here does not imply warmth, but rather the complete leveling of energy. In such a future, there is no preferred direction for energy to move because all directions look the same, and without energy gradients, there is no engine for change. Stars form because gravity compresses gas, raising temperature and pressure, but star formation requires dense pockets of matter, and over immense timescales, galaxies gradually use up their raw material, locking matter into stars, stellar remnants, and eventually into objects that no longer produce light. Existing stars slowly exhaust their nuclear fuel, transitioning into cooler and dimmer states, and new stars become increasingly rare as interstellar gas becomes scarce. Long before the final stages arrive, the universe already begins to appear darker, quieter, and more diffuse. Black holes, which are among the most stable structures known, also participate in this gradual fading because, according to modern physics, they emit extremely small amounts of radiation, losing mass over vast timescales, so even these dense objects are not truly permanent. The scale of time involved is difficult to visualize, stretching far beyond the current age of the universe, but the key feature is not the length of time, but the direction of change, which is always toward greater uniformity. Nothing dramatic needs to happen for heat death to occur, because it is simply the continuation of processes already underway. The universe does not collapse into nothing, and it does not suddenly go dark in a single moment, but instead becomes increasingly empty, sparse, and energetically flat. Motion still exists in a technical sense, but it becomes meaningless because nothing macroscopic can organize itself into complex patterns anymore. Chemical reactions become impossible because there is no free energy to drive them. Biological processes cannot occur because metabolism requires energy flow. Even simple mechanical processes fade because friction and radiation slowly drain all organized motion. What remains is a universe filled with extremely low-energy particles spread thinly across vast distances, drifting in near-thermal equilibrium. The word equilibrium here refers to a condition where all parts of a system share approximately the same energy, so there is no natural tendency for change in any particular direction. This state does not resemble death in a biological sense, but rather a kind of complete stillness at the largest scale. It is important to notice that this scenario does not rely on any assumption about intention, purpose, or meaning, but only on the statistical behavior of large numbers of particles following simple physical rules. The universe does not aim for heat death, and it does not avoid it, but rather moves in that direction because it is the most probable outcome of countless small interactions unfolding over time. From the perspective of human experience, which is shaped by rapid change, cycles, and limited lifespans, this future feels abstract and distant, but from a physical standpoint, it is a natural extension of processes that are happening right now, quietly, continuously, and without pause. As the universe drifts towards this evenly distributed state, an important question quietly arises, which is why time itself seems to have a direction at all. Because at the most basic level, the fundamental laws of physics do not strongly prefer a past over a future. Yet in everyday experience, time clearly feels as though it moves from order toward disorder, from structure toward diffusion. And this feeling is closely connected to the same process that leads toward heat death. Entropy does not simply describe the fate of stars and galaxies, but also describes why memories form in one direction, why causes precede effects, and why physical systems tend to move towards states that are more statistically common. A highly ordered configuration, such as a dense cloud of gas arranged just right to form stars, is extremely rare among all possible configurations of particles, while a dispersed uniform arrangement is vastly more common. When systems are allowed to evolve freely, they naturally drift toward these more common arrangements, not because they are guided, but because there are simply more ways for particles to be spread out than tightly organized. Over immense timescales, this statistical tendency becomes dominant. The arrow of time, in this sense, is not imposed from outside the universe, but emerges from the collective behavior of matter and energy. As long as large energy differences exist, change continues to occur, and as long as change occurs, time feels active. But when energy differences diminish, the processes that mark time also slow. Clocks, whether mechanical, chemical, or biological, rely on predictable transformations driven by energy flow. If no energy can be harnessed to drive transformation, then the concept of time loses its operational meaning, even if a mathematical parameter called time still exists in equations. In the far future of heat death, nothing dramatic announces this shift. There is no moment where time suddenly stops. Instead, the processes that once defined time gradually become less distinct, until the universe reaches a condition where nothing meaningful happens. Without events, time becomes indistinguishable from stillness. This does not require absolute immobility at the microscopic level. Particles may still move, quantum fluctuations may still occur, and tiny interactions may still take place, but none of these produce stable patterns, memories, or structures. From a physical perspective, the universe still exists, but from a functional perspective, it no longer does anything. The difference between existence and activity becomes important here. Heat death describes a universe that continues to exist but lacks the capacity for complexity. No stars ignite, no molecules assemble into organized systems, no long chains of cause and effect persist. Everything that once depended on contrast now lacks contrast. Even gravity, which organizes matter into large structures, becomes less influential when matter is spread extremely thin. Galaxies drift apart as space continues to expand. Local clusters slowly dissolve. Eventually, individual particles are separated by distances so vast that interactions become extraordinarily rare. The universe becomes dominated not by objects but by empty space. This emptiness is not absolute nothingness. It is a state filled with extremely low energy radiation and isolated particles. Yet this presence is so uniform that it behaves like absence. Nothing stands out. Nothing differentiates itself from its surroundings. This condition represents a kind of physical silence, not silence in the auditory sense, but silence as the absence of organized change. From the viewpoint of thermodynamics, this silence is stable. Once reached, there is no internal mechanism that can spontaneously rebuild large-scale structure, because doing so would require concentrating energy without an external source, and no external source exists. The universe becomes a closed system that has fully explored its possibilities. All accessible configurations lead back toward uniformity. In this way, heat death is not an ending event, but a limit, a boundary beyond which further evolution has no direction. It is the natural outcome of a universe that began in a highly ordered state and has been gradually relaxing ever since. To understand why the universe began in a highly ordered condition at all, it is useful to consider that order and disorder are not absolute qualities, but descriptions of probability. And the early universe appears to have started in a state where energy was extremely concentrated, even though matter itself was nearly uniform. This combination allowed gravity to later amplify tiny irregularities, gradually forming stars, galaxies, and clusters. But at the same time, it established a vast reservoir of usable energy differences. These differences are what have powered all physical activity since then. As the universe expands, space itself stretches, and this expansion steadily dilutes energy. Light traveling through expanding space gradually loses energy, shifting toward longer wavelengths. Matter becomes more widely separated. Temperature differences slowly decrease. None of this happens quickly. There is no threshold where conditions suddenly change. Instead, every moment resembles the previous one, with only a slight increase in overall smoothness. Over time, these tiny changes accumulate. The universe does not become cold in the everyday sense of feeling chilly. Rather, it approaches a state where temperature has little meaning, because temperature is only a useful concept when comparing regions that differ. When everything is nearly the same, temperature becomes a number without practical consequence. In this future, energy still exists, but it is locked into forms that cannot be extracted to perform work. Work, in physics, simply means organized transfer of energy that produces a change. A wind turning a turbine, a chemical reaction releasing heat, or an electrical current flowing through a circuit are all examples of work. Each of these requires an imbalance. When imbalances disappear, work disappears. Without work, there is no machinery, no chemistry, and no biological activity. The transition toward this condition is smooth and continuous. Stars gradually fade into dim remnants. White dwarfs cool into dark, inert objects. Neutron stars lose residual heat. Black holes slowly evaporate. Long after all luminous objects are gone, the universe still continues to evolve, but only in the sense that extremely slow decay processes proceed. Even protons, which appear stable over very long times, may eventually decay according to some theoretical models, further simplifying the contents of the cosmos. As complexity decreases, the variety of possible states also decreases. Early in cosmic history, the universe could support a vast range of structures and behaviors. In the far future, the range becomes narrow. Most possible configurations look almost identical. This narrowing is another way of describing increasing entropy. It is not chaos in the sense of randomness, but sameness. High entropy does not mean wildly fluctuating disorder, it means uniformity. This is an important distinction because everyday language often associates disorder with turbulence or agitation, but the ultimate high entropy state is calm, smooth, and featureless. The path toward heat death therefore resembles a gradual flattening of possibilities. Fewer things can happen, and the things that can happen become increasingly trivial. From a cosmic perspective, the era in which complex structures exist is brief. It occupies a small window between the hot, dense beginning and the cold, diffuse future. Within this window, galaxies, stars, planets, and living systems arise. Outside this window, the universe is either too energetic or too depleted to support complexity. This does not imply that the universe was designed to host complexity, nor that complexity is central to its purpose. It simply reflects how physical laws behave when energy is unevenly distributed. Complexity appears where conditions allow it. When conditions change, complexity fades. The heat death scenario does not describe a universe that fails. It describes a universe that follows its rules to their natural conclusion. There is no judgment embedded in this outcome. There is no sense in which the universe becomes worse. It simply becomes simpler. Over unimaginable durations, the richness of forms slowly collapses into a quiet monotony. This monotony is not dramatic. It is not catastrophic. It is the silent result of countless small transitions, each one almost indistinguishable from the last, unfolding steadily as the universe continues its long relaxation toward equilibrium. As complexity fades, the question of what it means for something to exist becomes more subtle. Because much of what humans intuitively associate with existence involves interaction, change, and persistence of structure. A star exists in the sense that it emits light and influences its surroundings. A living organism exists in the sense that it maintains internal organization through constant exchange of energy. A thought exists in the sense that neural activity forms a temporary pattern. In a high-entropy universe, these familiar modes of existence become rare or impossible. What remains are entities that persist only as isolated configurations of particles, without the capacity to produce sustained effects. From a physical standpoint, these entities still exist, but from a functional standpoint, they no longer participate in any larger process. This distinction between existence and relevance becomes important. Heat death does not erase the contents of the universe, it renders them inert. Everything is present, but nothing matters to anything else, because no interactions lead to lasting consequences.
cause and effect lose practical meaning not because causality is broken, but because causes no longer propagate into chains of complex outcomes. A particle may collide with another particle, but the result does not cascade into chemistry, biology, or structure formation. It dissipates almost immediately into uniform background energy. Over time, even these small interactions become increasingly rare as particles drift farther apart. The universe becomes a collection of extremely isolated events separated by vast regions of near emptiness. In this environment, the concept of history also changes. History, as commonly understood, is a record of irreversible transformations that build upon one another. A supernova leaves behind heavy elements. Those elements form planets. Planets host life. Life alters planetary environments. Each step depends on previous steps. In a high-entropy universe, such chains no longer exist. There are no meaningful records being created because there are no stable systems to store information. Memory, in physical terms, requires persistent structure. A book holds information because its pages retain specific patterns. A brain holds information because synaptic connections maintain particular configurations. If no structure can persist, information cannot accumulate. Without accumulated information, there is no meaningful past. This does not mean that earlier states never occurred. It means that nothing in the present refers back to them. The universe forgets itself, not through an active erasure, but through the absence of mechanisms that preserve distinctions. This forgetting is gradual. Long before heat death is complete, most records are already lost. Stars that once illuminated galaxies leave no trace. Civilizations, if they ever arise, fade without a mark. Even the cosmic background radiation slowly redshifts to wavelengths so long that it becomes practically undetectable. Eventually, nothing within the universe encodes a detailed account of its own origin. The universe still follows equations that describe its behavior, but no physical system exists to represent those equations or to interpret them. In this sense, the universe becomes self-contained and self-unaware, though awareness is not something the universe ever possessed in a literal sense. Awareness arises only within certain localized physical systems, such as brains. When such systems cannot exist, awareness cannot arise. The future universe is not empty of existence, but empty of experience. Experience requires organization. Organization requires energy flow. Energy flow requires gradients. Gradients disappear. This chain of dependence links consciousness indirectly to entropy. Entropy does not drive energy, and entropy does not target consciousness. They are simply connected through the conditions that make complex systems possible. The heat death scenario therefore describes not only a physical outcome, but also a limit on what kinds of phenomena can occur. It marks the boundary beyond which concepts like observer, memory, and process lose applicability. The universe does not become dead in the way a living organism dies. It becomes quiet in a deeper sense. Quiet as in the absence of ongoing differentiation. Everything blends into a single, nearly uniform condition. This uniformity is stable. Once achieved, there is no internal reason for it to change. The universe settles into a state where the distinction between something happening and nothing happening becomes increasingly blurred until, for all practical purposes, nothing happens at all.
The idea that the universe can approach a condition where nothing meaningful happens may feel abstract, but it follows directly from how physical laws treat large collections of particles over long periods. At small scales, motion never truly stops. Atoms vibrate, subatomic particles fluctuate, quantum fields exhibit constant activity. Yet these motions by themselves do not create structure. Structure requires coordination. It requires patterns that persist long enough to interact with other patterns. In a high-entropy universe, motion continues, but coordination disappears. Movements become statistically independent. One particle's behavior has almost no influence on another particle's behavior beyond extremely brief encounters. This independence prevents the formation of large-scale organization. It is similar to the difference between random drifting and collective flow. A river can carve a valley because its water moves in a correlated direction. A cloud of randomly moving droplets cannot. As entropy increases, more and more motion resembles the latter. The universe still contains activity, but that activity no longer combines into anything larger than itself. This helps clarify why heat death is not the same as absolute stillness. It is a state where motion exists, but usefulness does not. From a practical standpoint, usefulness means the ability to produce change that matters at some scale. In the far future, changes still occur, but none of them accumulate into anything enduring. They appear and vanish without consequence. Another way to think about this is through the idea of free energy. Free energy is the portion of energy that can be harnessed to do work. A system may contain enormous total energy, but if all of that energy is evenly spread, none of it can be directed. A calm ocean contains a vast amount of energy, but if the surface is perfectly flat and the temperature is uniform, there are no waves, currents, or temperature gradients to exploit. The future universe resembles this calm ocean. Energy is everywhere, but it cannot be shaped into purposeful motion. Over cosmic time, the amount of free energy steadily decreases. Early in the universe, free energy was abundant. Stars, galaxies, and life became possible. Later, free energy becomes scarce. Complexity becomes difficult. Eventually, free energy effectively reaches zero. At that point, the universe still exists as a physical system, but it has lost its capacity for transformation. This loss of capacity is the central feature of heat death. It is not about destruction, it is about exhaustion. Not exhaustion in an emotional sense, but in a thermodynamic sense. All accessible pathways for converting energy into organized change have been explored. Nothing remains that can be converted further. The universe has spent its initial energy differences. It has cashed in its potential for complexity. This framing avoids dramatic imagery. There is no cosmic catastrophe. There is no collapse or explosion. There is only a gradual approach toward a state that is increasingly uneventful. From any local perspective, the transition is imperceptible. There is never a moment where an observer would say that heat death has arrived. By the time conditions resemble heat death, observers can no longer exist. The universe does not witness its own quieting, it simply continues. This highlights an important asymmetry between physical description and experiential description. Physics can describe states that contain no experience. Experience cannot access such states. Heat death belongs entirely to the domain of description. It is a prediction about what physical systems do, not a scenario that can be observed from within. In this sense, heat death is less like an ending and more like a limit point in a mathematical model. The universe approaches it ever more closely without needing to reach a sharply defined final moment. This gradual convergence is consistent with how many physical processes behave.
Temperatures approach equilibrium asymptotically. Differences shrink but never need to become exactly zero. The same logic applies here. The universe becomes arbitrarily close to perfect uniformity, close enough that no macroscopic distinction remains. When this condition is reached, the universe has not disappeared, it has not been destroyed, it has become maximally simple. All that remains is a thin, diffuse, uniform distribution of energy and particles, drifting without direction, without structure, and without the possibility of new beginnings.
Within this extremely simple future, it is natural to wonder whether any kind of reversal could occur, whether randomness alone might eventually assemble something complex again, even if only briefly. But when examined carefully, this possibility becomes vanishingly small, not because it is forbidden by physical law, but because the number of ways for disorder to arrange itself vastly exceeds the number of ways for order to arise. In principle, particles moving randomly could momentarily form a low-entropy configuration, just as molecules in air could, by chance, cluster into a denser pocket. But the probability of such an event decreases exponentially with the size and complexity of the structure. A small fluctuation might briefly produce a slight density variation, but assembling something as elaborate as a star, a molecule, or a functioning brain purely through random motion in a high-entropy universe is so improbable that it effectively never happens within any meaningful timescale. The universe is not only large, it is also old. Yet even across unimaginable durations, some configurations remain so unlikely that they can be treated as impossible for practical purposes. This is a key distinction in physics. Possibility in principle does not imply relevance in reality. Heat death describes a universe where the overwhelming statistical weight favors uniformity at all times. Small deviations may occur, but they are tiny, short-lived, and inconsequential. They do not cascade into new eras of complexity. This is because cascades require feedback. Feedback requires energy gradients. Gradients are absent. Without feedback loops, nothing amplifies, everything damps out. Another factor that stabilizes the high-entropy state is expansion. As space continues to grow, particles become increasingly isolated. Even if a small fluctuation produces a local concentration, the surrounding environment is so empty and so uniform that the concentration quickly disperses. There is no surrounding reservoir of matter to feed growth. Growth requires both local concentration and external supply. Neither is available. This means that heat death is not a fragile equilibrium, it is robust. Once the universe enters this regime, it does not oscillate back into complexity. It remains simple. This irreversibility is closely tied to the same arrow of time discussed earlier. The arrow of time points toward states that are more statistically typical. High-entropy states are the most typical. Low-entropy states are special. The early universe was special. The far-future universe is typical. This asymmetry is one of the deepest features of cosmology. Physics can describe how systems evolve, but it does not fully explain why the universe began in such an unusually ordered condition. That question remains open. Heat death, however, does not depend on the answer. Regardless of why the universe started with low entropy, its subsequent evolution naturally increases entropy. The destination follows from the trajectory. From a human perspective, the idea that the universe ends in a featureless state can evoke a sense of loss. But this reaction reflects human values, not physical ones.
The universe does not possess preferences. It does not value complexity or simplicity. It does not seek richness or avoid monotony. It simply follows the statistical tendencies of large systems. Complexity is a temporary pattern that appears under certain conditions. When those conditions fade, complexity fades. This is not a failure. It is not tragic in a physical sense. It is neutral. The heat-death scenario therefore invites a shift in how endings are imagined. Instead of a dramatic finale, there is a gradual smoothing. Instead of a final moment, there is a long quieting. Instead of destruction, there is dilution. The universe does not collapse into nothing. It thins into near sameness. This thinning continues without milestone or announcement. Each moment resembles the previous one slightly more than the one before it. Differences shrink, distinctions blur. Over time, the universe becomes less a collection of objects and more a continuous background. In this background, nothing stands out enough to be called a thing in the everyday sense. Categories lose their usefulness. Words like star, particle, and space describe distinctions that no longer matter. All that remains is a simple physical presence extending across vast distances, changing in the most minimal way allowed by the laws that govern it.
At this stage of the universe, the distinction between foreground and background effectively disappears because nothing rises above the uniform baseline strongly enough to serve as a reference point. In earlier cosmic eras, objects could be identified because they contrasted with their surroundings. A star was bright against darkness. A galaxy was dense compared to empty space. A planet was a compact body orbiting a larger mass. These contrasts allowed systems to be defined, tracked, and studied. In a high-entropy universe, contrast fades. When everything is nearly the same, nothing can be isolated conceptually. This loss of contrast has deep implications for how physical description itself functions. Many physical quantities are defined relationally. Temperature is a comparison between energy states. Pressure is a measure of particle interactions within a region compared to another. Distance becomes meaningful when there are identifiable endpoints. When distinguishable endpoints vanish, distance becomes an abstract coordinate without physical significance. Space still exists in a mathematical sense, but it no longer contains landmarks. This means that geometry remains, but geography disappears. There is no meaningful sense of location because nothing occupies locations in a way that differs from anything else. The universe becomes homogeneous not only in composition, but also in meaning. This homogenization extends to time as well. Earlier, time was associated with change. Clocks ticked because something repeated. Systems aged because they transformed. In the far future, transformations are so minimal and so uniform that no process can function as a clock. One moment cannot be distinguished from the next by any internal marker. Time still exists as a parameter in equations, but it no longer corresponds to anything observable. This is not because time has ended, but because observation has ended. Without observers or observable processes, time loses operational content. It becomes a silent variable. This perspective reveals that many fundamental seeming aspects of reality, such as space, time, and objects, are deeply connected to the existence of structure. When structure dissolves, these concepts do not vanish, but they lose their practical role. They remain as abstract descriptions of an underlying mathematical framework. The heat-death universe can therefore be thought of as a universe that is still mathematically well-defined, but physically uneventful.
Nothing violates physical law. Nothing dramatic occurs. Everything simply settles into the most statistically stable configuration. It is also worth noting that this final state does not require the universe to reach absolute perfection. It only needs to become close enough to uniformity that no macroscopic process can extract energy. Absolute zero temperature may never be reached. Perfect equilibrium may never be achieved. But these ideals are not necessary. Practical equilibrium is sufficient. Practical equilibrium means that any remaining differences are too small to matter. From any conceivable internal perspective, the universe is done. This notion of being done is subtle. It does not imply that a goal has been accomplished. It implies that there is nothing left to do. All available pathways for change have been exhausted. All gradients have flattened. All engines have stalled. The universe does not recognize this condition. It does not label it. It does not reflect on it. The description exists only in theoretical models. From within, there is no awareness of completion. The universe simply persists. This persistence, however, is qualitatively different from earlier persistence. Earlier, persistence was dynamic. Things persisted by constantly changing. Stars burned fuel. Planets orbited. Life metabolized. In the far future, persistence is static. Things persist by not doing anything. Existence becomes passive. This shift from active persistence to passive persistence marks a deep transformation in the character of reality. Yet even this transformation is gradual. There is no dividing line, no epoch where the universe crosses from active to passive in a single step. The activity level declines continuously. At every stage, the universe resembles the previous stage slightly more than it resembles any distant past. This continuity ensures that heat death is not an event, but a direction toward less distinction, less contrast, less structure, and less possibility. This gradual fading of distinction invites a deeper consideration of what it means for laws of physics to operate in a universe where nothing noticeable happens, because laws are often understood through the patterns they generate, and when patterns disappear, the presence of law becomes less intuitive. In earlier eras, physical laws expressed themselves through regularities that could be observed. Objects fell under gravity, light bent near massive bodies, atoms combined into molecules. These regularities made laws feel active. In a high-entropy universe, laws still apply, but their consequences no longer organize matter into visible patterns. The laws do not turn off, they simply no longer produce complexity. Gravity still exists, but there are no dense clumps to pull together. Electromagnetic interactions still exist, but there are no bound systems to sustain stable chemistry. Quantum behavior still exists, but it does not assemble into macroscopic order. The universe continues to obey its rules, but the rules lead only to sameness. This highlights an important feature of physical law. Laws do not guarantee interesting outcomes. They constrain what is possible. The richness of phenomena depends on initial conditions and available energy gradients. When gradients vanish, the space of interesting possibilities collapses, even though the laws remain unchanged. This distinction helps explain why heat death does not require any modification of known physics. It arises naturally from physics as currently understood. No special mechanism is needed to shut the universe down. There is no cosmic switch. The same equations that describe star formation also describe its eventual cessation. The difference lies entirely in the distribution of energy. Over time, distributions flatten. When they are flat enough, nothing new happens. Another subtle implication of this future concerns randomness. Early in cosmic history, randomness can generate variation that is then shaped by physical constraints into structure. For example, random density fluctuations become galaxies because gravity amplifies them. In a high-entropy universe, randomness still produces tiny variations, but nothing amplifies them. Randomness becomes sterile. It produces noise without consequence. This contrasts with the common idea that randomness is inherently creative. Randomness alone does not create complexity. It requires a context where some variations are preserved and built upon. Preservation requires stability. Stability requires energy flow. Without these, randomness produces only transient deviations that quickly dissolve. The far future universe is therefore not chaotic in a lively sense, it is statistically quiet. Fluctuations exist, but they do not accumulate. Another way to view this is through the concept of phase space, which refers to the set of all possible states a system can occupy. Early in the universe, phase space included a vast range of complex configurations. Over time, the system moves into regions of phase space dominated by simple configurations. Once there, most neighboring states are also simple. Movement within this region does not lead back to complexity. The system wanders within a narrow band of similar states. This wandering continues indefinitely, but it never escapes into the rich regions of phase space that existed earlier. From a macroscopic viewpoint, nothing changes. From a microscopic viewpoint, there is endless but trivial motion. This separation between microscopic activity and macroscopic stasis is one of the defining characteristics of heat death. It clarifies how a universe can be active and inert at the same time, depending on the scale of description. At very small scales, there is always motion. At large scales, there is effectively none. The large-scale perspective is the one relevant to structure, information, and experience. Since experience depends on macroscopic organization, the heat-death universe contains no experience, even though it contains activity. This again emphasizes that experience is not a fundamental property of matter, but an emergent property of certain organized arrangements. When those arrangements cannot form, experience cannot occur. The universe does not notice this loss. There is no global awareness to register the absence of awareness. The universe simply exists in a simpler mode. Over immense durations, this mode remains stable. Nothing pushes it out of it. Nothing steers it toward a new beginning. Heat death, therefore, represents a one-way settling into maximal simplicity, guided not by intention, but by probability.
When thinking about this long settling into simplicity, it can be helpful to consider how similar patterns appear at much smaller scales, because the same statistical tendencies operate everywhere. A hot cup of liquid placed in a cooler room gradually cools until it reaches the room's temperature. It does not spontaneously reheat itself. The molecules in the liquid continue to move, but their motion becomes distributed in a way that matches the surroundings. The cup still exists, the room still exists, but the process that once produced noticeable change has ended. The cooling of the cup is a local example of the same principle that governs the future of the universe. The difference lies only in scale. In both cases, systems move toward equilibrium. In both cases, equilibrium corresponds to a condition where macroscopic change ceases. This analogy is imperfect, but it captures the central idea. The universe can be understood as an enormous system placed inside nothing else,
evolving toward its own internal equilibrium. There is no external environment to supply new gradients. Everything that can happen must happen using what is already inside. Once those internal differences are smoothed out, the evolution becomes trivial. This framing avoids the idea of a cosmic deadline. There is no finish line, there is only gradual convergence. Another subtle point concerns the word future. In everyday language, future implies something that will be experienced, but in the context of heat death, future describes a theoretical extension of physical evolution beyond any possible experience. It is a future without observers. This does not make it less real in a physical sense. It simply places it outside experiential relevance. Physics routinely describes processes that occur without being observed. Most atomic interactions in the universe are never witnessed. Heat death belongs to this category. It is a description of what physical systems tend to do, not a story about what someone will see. This distinction helps maintain a neutral perspective. There is no need to imagine a lonely observer floating in a dark void. Such an observer cannot exist under those conditions. The correct picture is more abstract. The universe transitions into a regime where the concept of observer has no physical support. Another aspect of this scenario concerns symmetry. Early in cosmic history, many symmetries were broken. Forces differentiated. Particles acquired distinct properties. Matter separated from radiation in important ways. These symmetry breakings allowed diverse structures to exist. Over time, some distinctions blur again, not because symmetries are restored in a fundamental sense, but because differences become irrelevant. When all temperatures are nearly equal, the distinction between hot and cold loses meaning. When all densities are nearly equal, the distinction between dense and diffuse loses meaning. The universe becomes symmetric in a practical sense. Everything looks the same everywhere. This practical symmetry is a hallmark of heat death. It does not require a return to some primordial state. It is a new state, characterized by extreme dilution rather than extreme concentration. The early universe and the heat death universe are both simple, but in opposite ways. One is simple because everything is compressed. The other is simple because everything is spread out. Complexity emerges in between. This reinforces the idea that complexity is not fundamental. It is a transient feature that emerges under particular conditions. The universe is mostly simple. It only passes through a complex phase. This complex phase happens to be the one we inhabit. That fact feels important from a human perspective, but it does not carry special weight in the broader physical description. The laws of physics do not privilege this era. They treat all eras equally. The heat death scenario is therefore not a story about loss. It is a story about typical behavior. Large systems tend to move toward states that occupy the largest portion of their possible configuration space. Those states are simple. Over enough time, simplicity dominates. The universe follows this tendency, quietly, steadily, and without exception.
Considering this quiet dominance of simplicity, it becomes possible to reframe the entire history of the universe as a long transition between two simple conditions, with a brief, complex interval in between. At one extreme lies the early, dense, nearly uniform state. At the other extreme lies the late, diffuse, nearly uniform state.
Both are characterized by limited structural diversity. The difference between them is the direction in which energy is distributed. In the early universe, energy is concentrated. In the late universe, energy is diluted. Complexity emerges during the process of redistribution. This reframing removes the sense that the universe is on a narrative arc, with a beginning, middle, and end in a dramatic sense. Instead, it follows a relaxation curve. A system begins far from equilibrium. It gradually relaxes. Eventually, it becomes close to equilibrium. Everything in between is a consequence of that relaxation. Galaxies, stars, planets, chemistry, and life are not central milestones, they are intermediate byproducts. This perspective can feel impersonal, but it is consistent with how physical explanations generally operate. They describe tendencies, not intentions. Another implication of this view concerns meaning. Physical models do not assign meaning to states. They describe relationships between variables. Heat death is not meaningful or meaningless. It is simply a description of a statistical outcome. Meaning arises only within systems capable of representation, evaluation, and memory. These systems exist temporarily. When they cannot exist, meaning does not exist either. This does not invalidate meaning where it does exist, it simply limits its scope. Meaning is local and transient, like complexity itself. The universe does not accumulate meaning over time. It temporarily hosts islands of meaning. These islands form, change, and dissolve as conditions allow. In the heat death regime, no islands remain. Another subtle feature of this scenario is that it challenges the intuitive idea of permanence. It is common to think of fundamental particles or space-time itself as permanent. But permanence in physics often means extremely long-lived rather than eternal. Protons may decay, black holes may evaporate, even space-time may have properties that change over unimaginable durations. Heat death is therefore not necessarily a final frozen snapshot. It is better understood as a long-lasting regime. The universe may continue to evolve in ways that are currently unknown, but any such evolution would still be constrained by the lack of free energy. Without free energy, new forms of complexity cannot arise, regardless of the detailed microphysics. This makes heat death a robust conclusion across many possible future theories. Even if certain details change, the overall tendency toward equilibrium remains. It is also important to avoid imagining heat death as a single moment in the future. There is no universal clock counting down to it. Instead, different regions approach equilibrium at different rates. Locally, stars burn out. Locally, galaxies fade. There is no synchronized cosmic shutdown. The process is patchy and asynchronous, yet globally, the trend is the same everywhere. Over time, more and more regions resemble equilibrium. Eventually, almost all regions do. The universe becomes dominated by near equilibrium conditions. The remaining pockets of structure become increasingly isolated. Eventually, they too fade. This slow and unsynchronized nature reinforces the idea that heat death is not an event, but a statistical dominance, a point where almost all accessible states of the universe are simple. The universe does not cross into a new phase, it drifts into a broad plateau. Once on this plateau, there is no downhill slope left. the system has reached the flattest part of its landscape. From there, it wanders without direction, without building anything new, and without returning to complexity.
As the universe wanders within this flat landscape of near equilibrium states, the notion of possibility itself becomes constrained in a very specific way. Possibility is often imagined as an open field of potential outcomes, but in physical systems, what is possible is always shaped by energy availability. When free energy is abundant, many outcomes can be realized. When free energy is scarce, most outcomes become inaccessible. In the heat-death regime, almost all outcomes that involve sustained organization are inaccessible. The space of possibilities collapses toward trivial rearrangements. Particles may exchange places. Tiny fluctuations may appear and disappear, but the set of possible macroscopic configurations becomes extremely narrow. This narrowing of possibility is not imposed by a rule. It emerges from the absence of usable energy. This provides a deeper understanding of why complexity is fragile. Complexity is not protected by any fundamental principle. It persists only as long as conditions support it. Once those conditions fade, complexity dissolves naturally. This dissolution does not require any destructive force. It requires only the quiet absence of construction. Over time, things fall apart simply because nothing holds them together. Another important implication concerns predictability. In everyday contexts, predictability is associated with regular patterns. The motion of planets is predictable. The oscillation of a pendulum is predictable. In the far future universe, predictability takes on a different form. At the microscopic level, motion may still follow probabilistic rules. At the macroscopic level, however, almost nothing happens, and therefore almost nothing needs to be predicted. The best prediction is that future states will resemble present states extremely closely. The universe becomes predictable in a trivial way. This trivial predictability is a hallmark of equilibrium. It is not the predictability of clocks, but the predictability of sameness. This also affects how uncertainty functions. Uncertainty normally reflects incomplete knowledge about a changing system. When systems barely change, uncertainty becomes irrelevant. There is little to be uncertain about. The universe is simple. Its simplicity is stable. This stability does not imply rigidity. It implies that deviations do not grow, they fade. The universe is like a surface where any small bump slowly flattens. Over long times, the surface remains smooth. This flattening tendency is the practical expression of increasing entropy. Another aspect of this future concerns scale. At human scales, heat death is unimaginable. At cosmic scales, it is ordinary. This mismatch highlights how deeply human intuition is shaped by mid-scale phenomena. Humans evolved in an environment where energy flows are abundant, gradients are steep, and change is constant. The brain expects activity. It interprets inactivity as unusual. On cosmic scales, the opposite is true. Activity is a temporary phase. Inactivity is the default. The universe spends most of its existence close to equilibrium. This perspective can feel counterintuitive, but it follows directly from statistical reasoning. Large systems spend most of their time in the most probable states. The most probable states are the most uniform ones. Therefore, the universe spends most of its existence being uniform. The complex era is brief by comparison.
This does not make the complex era insignificant in a physical sense. It simply places it in context. The universe does not build toward complexity and then lose it. It relaxes from an unusual beginning, passing through a complex interval along the way. The heat death scenario therefore completes a long arc of relaxation. It does not close a story, it completes a statistical process. Once complete, the process does not reverse, not because reversal is forbidden, but because reversal is overwhelmingly unlikely. The universe settles into a mode of existence where nothing accumulates, nothing organizes, and nothing persists in structured form. What remains is a thin, even, quiet presence, governed by the same laws as before, but expressing them in the simplest possible way.
As the universe settles into this regime where almost all large-scale possibilities have collapsed, it becomes useful to examine more carefully the relationship between structure and time, because time, as experienced, is not an independent backdrop, but a byproduct of change within structured systems. When structures exist, they undergo sequences of transformations. These sequences can be ordered. That ordering gives rise to the sensation of before and after. In a universe where structure cannot persist, sequences cannot be sustained. Without sustained sequences, temporal ordering loses its practical foundation. This does not mean that the mathematical parameter called time disappears. It means that nothing uses it. Earlier, clocks were mentioned as devices that track repetitive change. A swinging pendulum, an oscillating atom, a vibrating crystal. All of these depend on stable systems that cycle through states. In the heat-death regime, such cycles cannot be maintained. Any local oscillation quickly dampens into the background. Without cycles, there are no ticks. Without ticks, time cannot be measured internally. From inside such a universe, there is no sense of duration. There is no accumulation of moments. There is only a static condition that persists. This reveals that experienced time is deeply conditional. It requires ongoing differentiation. It requires systems that can hold one state long enough to compare it with another. When everything dissolves into uniformity, comparison becomes impossible. Even if microscopic events still occur, there is nothing that records them. No memory forms, no trace persists. Events happen, but they do not become history. They vanish as soon as they occur. In this sense, the future universe is not timeless. It is time without memory. Time without memory is indistinguishable from timelessness. This distinction is subtle but important. It shows that time does not need to stop for the universe to become effectively timeless. It only needs to lose the structures that give time operational meaning. The same logic applies to identity. Objects have identity because they persist as distinguishable entities. A star is the same star from one moment to the next because its internal structure remains mostly intact. In the heat-death regime, nothing persists in this way. Configurations change, but they do not maintain coherence. Without coherence, identity dissolves. There are no enduring things, only transient arrangements. This again does not require annihilation. It requires only the absence of stabilizing processes. Stability is a dynamic achievement. It is not the default state. It must be maintained by energy flow. When energy flow ends, stability ends. What remains is continuous microscopic motion without macroscopic continuity. This perspective unifies several earlier ideas: loss of complexity, loss of memory,
loss of time experience, and loss of identity are not separate phenomena. They are different expressions of the same underlying condition: absence of sustained structure. Heat death is therefore best understood not as a particular temperature, not as a particular darkness, and not as a particular emptiness, but as a structural condition, a condition where no arrangement can remain organized long enough to matter. In such a universe, nothing builds, nothing accumulates, nothing evolves. The universe still exists, it still follows physical law, but it no longer hosts processes that can be meaningfully described as happening. Everything reduces to quiet, statistically uniform motion, continuing without direction, without development, and without internal reference points.
When structure can no longer persist, the concept of scale itself begins to lose clarity, because scale depends on the ability to group components into higher-level units. A molecule is many atoms behaving as a unit. A star is many particles bound into a single object. A galaxy is many stars organized by gravity. Each level of scale relies on stable relationships. In the heat-death regime, such stable relationships do not form. Without stable groupings, there is no clear boundary between small and large. Everything exists at essentially the same level, isolated or weakly interacting particles embedded in uniform space. This flattening of scale contributes to the overall simplicity of the universe. There are no layers of organization. There is no hierarchy. There is only a vast collection of similar microstates. Earlier in cosmic history, the universe could be described at many levels. One could speak about atoms, molecules, cells, organisms, planets, stars, and galaxies. Each level had its own regularities. In the far future, only the most basic level remains relevant. Higher-level descriptions no longer apply because nothing behaves as a coherent whole long enough to justify them. This shift has implications for how physical explanation itself functions. Much of science relies on effective theories. An effective theory describes behavior at a certain scale without tracking every microscopic detail. Thermodynamics describes gases without following individual molecules. Biology describes organisms without tracking every atom. These approaches work because higher-level patterns exist. When higher-level patterns vanish, only fundamental descriptions remain meaningful. The universe becomes describable only in terms of its most elementary components and their statistical behavior. Even then, the descriptions become trivial because the behavior is uniform. This suggests that complexity is not only about the presence of many parts, but about the presence of stable relationships among parts. Without relationships, multiplicity alone does not produce richness. A trillion isolated particles are not more complex than a million isolated particles, if none of them form structures. Complexity arises from organization, not quantity. The heat-death universe may contain enormous numbers of particles, but they do not combine into anything interesting. This further clarifies why heat death is not emptiness. It is fullness without organization. It is content without structure. It is presence without pattern. Another subtle consequence of this state concerns explanation itself. Explanation usually involves showing how one pattern gives rise to another. If no patterns exist, explanation loses its subject matter. The universe still obeys equations, but there is little left to explain in a meaningful sense. Everything behaves as expected. Everything behaves the same way everywhere. There are no anomalies, no emergent phenomena, no surprises.
This does not mean that physics becomes false. It means that physics becomes boring in a technical sense. Boring not as a judgment, but as a description of minimal informational content. The universe carries almost no information. Information in physical terms is related to distinguishability. When everything is similar, information content is low. The early universe had low information because it was simple. The middle universe has high information because it is structured. The late universe returns to low information because it is simple again, but in a different way. This arc from simple to complex to simple mirrors the arc from low entropy to increasing entropy to high entropy. Simplicity can exist at both ends, but for opposite reasons. Understanding this symmetry helps remove any temptation to see heat death as a special catastrophe. It is simply one side of a broader pattern. The universe begins simple, it becomes complex, it becomes simple again. The details differ, but the overall shape remains. There is no hidden message in this pattern. It does not imply purpose. It does not imply design. It describes how large systems behave when left to their own dynamics. The universe follows its dynamics. Heat death is what that looks like in the long run. As the universe continues in this simplified condition, it becomes increasingly clear that what once felt fundamental, such as motion, interaction, and change, were always dependent on underlying imbalances and not intrinsic features of existence itself. In earlier eras, imbalance was everywhere. Hot contrasted with cold, dense contrasted with sparse, fast contrasted with slow. These contrasts created direction, they created flow, they created development. In the far future, contrasts become negligible. Without contrast, direction loses meaning. Motion may still occur at microscopic scales, but it does not organize into flows. Interactions may still occur, but they do not propagate into chains. Change may still occur, but it does not accumulate into history. The universe enters a mode where activity exists only in the most minimal sense. This suggests that stillness is not the absence of motion, but the absence of organized motion. From this perspective, heat death is a transition from organized activity to unorganized activity. The universe does not freeze, it relaxes. This relaxation removes all large-scale coherence. Coherence is what allows separate events to become parts of a larger process. Without coherence, events remain isolated. Isolated events do not build worlds, they do not form systems, they do not generate narratives. They appear and vanish without consequence. Over long durations, this absence of consequence defines the character of reality. Nothing leads anywhere. Nothing results in anything else. The universe does not move toward a goal. It simply persists in a condition where goals are no longer physically expressible. This highlights a subtle difference between persistence and continuation. Earlier, the universe continued by transforming. Later, it persists by remaining almost unchanged. Persistence without transformation becomes the dominant mode of existence. This mode is stable because there is no internal mechanism that can push the universe out of it. Any small deviation dissolves back into uniformity. In this sense, heat death represents the deepest form of stability that a closed physical system can achieve. It is not a balance between competing forces, it is the absence of competition altogether. Nothing is trying to overcome anything else. Nothing is being driven. Nothing is resisting. The universe is not at rest because it is restrained. It is at rest because there is nothing left to move it in any organized way. This condition does not imply completion in a narrative sense. It implies saturation. All possible large-scale rearrangements that rely on energy gradients have already occurred. What remains are only micro-level rearrangements that do not scale upward. The universe becomes a background without foreground, a field without figures, a presence without structure. This is not an ending scene. It is a long, indefinite continuation of near sameness. The universe remains, but it no longer expresses variety. It no longer expresses complexity. It expresses only the simplest version of what it can be under its own laws.
In this regime of near sameness, the distinction between possibility and impossibility becomes mostly irrelevant, because while many configurations may still be possible in principle, almost none are reachable in practice. Reachability depends on pathways. Pathways depend on gradients. Gradients no longer exist. This means that the universe is not constrained by strict prohibitions, but by the absence of means. Nothing forbids a complex structure from existing. There is simply no process capable of producing or sustaining one. This absence of means is more fundamental than any rule. It explains why the future universe is simple without requiring additional laws. Simplicity emerges because construction requires resources, and resources are no longer available in usable form. Earlier, stars acted as engines that concentrated energy. Later, black holes acted as long-term reservoirs. Eventually, even these reservoirs fade. When all engines stop, no new engines can be built. The universe enters an engineless state. This concept helps clarify the difference between potential energy and accessible energy. Potential energy can exist as a number in an equation. Accessible energy is energy that can be converted into organized change. Heat death occurs when accessible energy effectively reaches zero, even though total energy remains. This distinction is central. The universe is not empty of energy, it is empty of usable energy. Another implication concerns causation. Causation is meaningful when causes reliably lead to effects that persist or propagate. In a high-entropy universe, causes still produce effects, but effects do not lead to further effects in extended chains. Causation becomes shallow. Events have no depth. A shallow causal world is one where nothing builds upon anything else. This again ties back to the absence of structure. Structure is what allows causes to echo forward. Without structure, causation collapses into isolated interactions. This does not violate physical law. It reflects a change in context. The same laws operate, but the environment no longer supports complex outcomes. The universe becomes a place where laws are expressed only in their simplest consequences. Over time, this simplicity becomes all that exists, not because something removed complexity, but because nothing sustains it. The disappearance of complexity is therefore passive. It happens by default. This passivity is one of the most striking features of heat death. There is no cosmic force pushing toward simplicity. There is only the absence of forces that push toward organization. Organization requires continuous effort. Simplicity does not. When effort becomes impossible, simplicity dominates.
This framing removes any dramatic tone from the scenario. Heat death is not a disaster. It is not a collapse. It is the quiet outcome of a universe that has gradually spent its ability to differentiate itself. The universe does not mourn this state. It does not recognize it. It simply exists within it. From a physical standpoint, nothing is wrong. The universe is behaving exactly as expected. From a conceptual standpoint, the universe has reached the simplest expression of its existence.
As the universe remains in this simplest expression, it becomes useful to reconsider the idea of change itself, because change is often assumed to be an inherent feature of reality. Yet what has gradually become clear is that change depends on conditions, not on necessity. Change requires differences. It requires something to move towards something else. It requires unevenness. When everything is even, change loses its direction. Motion may still occur, but motion without direction is not development. It is not progression. It is not evolution. It is merely fluctuation. This distinction separates dynamic history from static persistence. Earlier in the universe, change had direction because gradients existed. Energy flowed downhill. Structures formed, transformed, and dissolved. In the heat-death regime, there is no downhill. All directions are flat. This means that while microscopic states continue to vary, the macroscopic state remains the same. Nothing meaningful accumulates. Nothing trends. Nothing grows or decays in any noticeable way. The universe becomes temporally flat in the same sense that it becomes spatially uniform. One moment does not differ from the next in any important respect. This temporal flatness does not imply a frozen snapshot. It implies endless repetition of near-identical conditions. The universe does not settle into a single configuration and stay there forever. It continuously explores many similar configurations, but all of these configurations look the same at large scales. This exploration is random, not purposeful. It does not lead anywhere. It simply continues. This reveals a deeper feature of physical systems. Stability at large scales does not require stillness at small scales. It requires only that small-scale activity does not organize into large-scale patterns. The heat-death universe satisfies this condition. Small-scale motion persists, large-scale structure does not. This separation of scales allows the universe to be both active and inert at the same time. From the inside of a particle, there is motion. From the perspective of any macroscopic description, there is nothing happening. This duality is essential to understanding why heat death is subtle rather than dramatic. There is no single moment where activity ceases. Activity never ceases. It simply becomes irrelevant. Relevance requires scale. When scale collapses, relevance collapses. Another implication of this is that questions about what happens next lose their usual meaning. Normally, asking what happens next assumes that something different will happen. In the heat-death regime, next looks like now looks like before. All moments are effectively interchangeable. This does not mean that time loops. It means that time has no landmarks. Without landmarks, temporal navigation becomes meaningless. The universe still has a future in a mathematical sense. It does not have a future in a narrative sense. Nothing new unfolds. Nothing builds toward anything else. The universe exists in a steady condition of minimal expression.
This condition is not imposed from outside, it emerges naturally from the long history of relaxation. The universe has slowly relaxed for billions upon billions of years. Heat death is simply the state where relaxation has gone as far as it can go. Beyond this point, relaxation has no further effect. The universe has reached its most relaxed form.
In this most relaxed form of existence, the universe no longer supports distinctions that once seemed essential, and this invites a reconsideration of what it means to describe reality at all, because description depends on contrast. To describe something is to separate it from something else. To name an object is to distinguish it from its surroundings. In a universe where everything is nearly identical, description becomes redundant. Any statement applies equally everywhere. There are no special regions, no unique objects, no notable events. Language, which evolved to track differences, loses its function. This does not mean that words become false. It means they become unnecessary. The universe does not require narration. It does not require labels. It does not require categories. These were tools used by localized, complex systems to navigate a structured environment. When structure disappears, the tools become obsolete. This highlights that many concepts humans treat as fundamental are actually contingent. They depend on a particular range of physical conditions. Object, boundary, system, process, and history are not universal necessities. They are features of a temporary cosmic phase. In the heat-death regime, none of these features are present in a meaningful way. What remains is physical presence without articulation. Another subtle consequence concerns explanation chains. Earlier, one could explain phenomena by tracing sequences of cause and effect. A star formed because gas collapsed. Gas collapsed because gravity overcame pressure. Pressure arose because of thermal motion. Each step referred to a previous step. In a high-entropy universe, such chains are extremely short. Events do not lead into extended sequences. Explanation collapses into immediate interactions. Nothing deeper is happening. This does not indicate a loss of depth in reality itself. It indicates a loss of layered structure. Depth in explanation arises from nested levels of organization. Without nested levels, depth disappears. The universe becomes shallow in a structural sense. Shallow does not mean simple-minded. It means lacking hierarchy. Everything exists on essentially the same footing. Another implication concerns novelty. Novelty arises when new combinations form and persist. In the heat-death regime, combinations may form momentarily, but they do not persist. Without persistence, novelty has no impact. It appears and vanishes without trace. Over time, the universe exhibits no accumulation of novelty. This is another way of saying that evolution has stopped. Evolution, in its broadest sense, is cumulative change. Cumulative change requires memory. Memory requires structure. Without structure, there is no memory. Without memory, there is no accumulation. Without accumulation, there is no evolution. The universe still exists. It still changes microscopically, but it no longer evolves in any meaningful way. This distinction between change and evolution is important. Change can occur endlessly. Evolution requires direction and accumulation. Heat-death removes both. The universe enters a mode where existence continues without development. This mode is not tragic. It is not celebratory. It is neutral. It is simply the long-term behavior of a closed physical system. The universe has no awareness of having entered this mode. It does not mark a transition. It does not cross a finish line. It simply finds itself in a condition where nothing builds, nothing deepens, and nothing differentiates. And in that condition, it remains. In this condition of near total uniformity, even the idea of background becomes unnecessary, because background only has meaning when something stands in front of it. Earlier, the universe contained contrasts. Objects stood out against space. Events stood out against silence. Patterns stood out against noise. In the heat-death regime, nothing stands out. Everything blends. The distinction between signal and noise disappears because there is no signal. There is only a continuous, low-level physical presence. This does not mean that the universe becomes empty. It means that presence loses shape. Presence loses edges. Without edges, nothing can be isolated. Without isolation, nothing can be treated as a thing. The universe becomes an undivided field rather than a collection of parts. This shift is not abrupt. It is the endpoint of a long erosion of boundaries. Boundaries once existed because forces and energies maintained them. When maintenance becomes impossible, boundaries dissolve. The dissolution of boundaries does not require destruction. It requires only neglect. Without ongoing support, all structures gradually blur into their surroundings. This blurring is the dominant visual metaphor for heat death, though even visual metaphor becomes inappropriate because there is no observer to see anything. The universe does not look like anything. It simply exists in a minimal configuration. Another implication concerns differentiation. Differentiation is the process by which one region becomes distinct from another. It requires energy input. In the far future, no such input is available. Therefore, differentiation cannot occur. Any tiny difference that arises quickly smooths out. The universe behaves like a perfectly calm surface. A small ripple may appear. It fades immediately. No waves propagate. No patterns grow. This reinforces the idea that heat death is a condition of maximum smoothing. Smoothing is more accurate than cooling. Cooling implies temperature. Smoothing implies loss of variation in all properties. Temperature, density, pressure, composition, and motion all become nearly uniform. When everything is nearly uniform, description itself becomes trivial. One description applies everywhere. The universe becomes easy to describe and impossible to differentiate. This simplicity does not feel like simplicity from the inside because there is no inside perspective. It is only simple from an abstract viewpoint. From that viewpoint, the universe has reduced itself to its most generic expression, not because it chose to, not because it was directed, but because that expression occupies almost all of the available physical possibility space. Heat death is therefore not a destination in the way a place is a destination. It is a statistical attractor. The universe drifts toward it because almost all paths lead there. Once near it, there are no meaningful paths leading away. The universe remains in this state, not as a frozen corpse, not as a ruined system, but as a quiet, persistent physical presence, continuing without development, without differentiation, and without internal landmarks. In this quiet persistence, the difference between existence and non-existence becomes harder to articulate, because many of the features that normally justify calling something existent are absent. Objects no longer persist. Events no longer accumulate. Histories no longer form. Yet the underlying physical substrate remains. Particles, fields, and space-time continue.
This suggests that existence, at its most basic level, does not require activity, organization, or experience. It requires only that physical quantities continue to have values. Heat death, therefore, does not describe a universe that has vanished. It describes a universe that has been reduced to bare physical continuity. Nothing more is added, nothing more is removed. The universe remains as a minimal fact. Another way to approach this is to consider that earlier in cosmic history, existence had layers. There was the existence of particles, the existence of atoms, the existence of stars, the existence of living systems. Each layer added new kinds of persistence. In the far future, these higher layers collapse. Only the lowest layer remains relevant. This collapse does not involve destruction, it involves loss of support. Higher layers depend on specific conditions. When those conditions fade, the layers fade. What remains is the simplest layer that does not depend on anything else. This perspective again emphasizes that complexity is conditional. Simplicity is robust. Another implication concerns difference across space. Earlier, different regions of the universe had different histories. Some formed galaxies, some remained emptier, some hosted heavy elements, some did not. In the heat death regime, these historical differences no longer manifest. Even if they once existed, nothing in the present reflects them. The universe forgets not by erasing the past, but by losing all physical traces of it. Forgetting is not an action, it is a consequence of uniformity. When everything is the same, nothing encodes variation. This is a deeper kind of forgetting than loss of memory. It is loss of distinguishability. The universe still contains everything in a trivial sense, but nothing is labeled, nothing is marked, nothing carries a signature. All identities dissolve into sameness. This sameness is stable. There is no internal pressure toward redifferentiation. The universe does not cycle, it does not rejuvenate, it does not reorganize. It persists in minimal form. This minimal form is not special, it is not privileged. It is simply what remains when all other forms can no longer be sustained. Heat death, in this sense, is not about death, it is about reduction. Reduction to the lowest common denominator of physical existence. And at that level, there is nothing left to lose.
At this point in the conceptual progression, it becomes clear that heat death is less a story about the end of things and more a story about the exhaustion of conditions. Nothing is actively removed from the universe. No force sweeps through and erases structures. Instead, the circumstances that once allowed structures to arise gradually disappear. This distinction matters because it shifts the focus from destruction to absence of construction. Earlier, the universe constantly built, stars assembled, atoms combined, systems stabilized. All of this required continuous access to free energy. When free energy fades, building fades. What already exists slowly decays. What decays is not replaced. Over time, the balance shifts entirely toward decay without renewal. Eventually, only decay remains, and long after decay has completed, only uniformity remains. This framing avoids imagining heat death as a moment of collapse. It is not a collapse. It is a long asymmetry between building and unbuilding that gradually reaches its extreme. Another implication concerns the role of chance. Earlier, chance variations could sometimes be captured and amplified by physical processes. A random fluctuation might become the seed of a star or a galaxy. In the heat-death regime, chance still produces fluctuations, but none are captured. There are no mechanisms to lock them in. Chance becomes sterile. It produces noise without consequence. This again reinforces the idea that randomness alone does not generate complexity. Randomness plus structure generates complexity. When structure is gone, randomness is inert. The universe still contains uncertainty at small scales. It does not contain creativity. Another subtle point concerns finality. Humans often imagine endings as definitive moments. Heat-death offers a different model. It is an endless continuation in a minimal state. There is no last event. There is no final change. There is no moment after which nothing exists. There is only an era after which nothing new happens. This distinction is crucial. The universe does not terminate, it settles. It enters a regime of permanent monotony. Permanent here means not absolutely eternal in a philosophical sense, but effectively unchanging across any meaningful duration. If future physics were to reveal unexpected behavior at extremely long timescales, it would still have to operate without free energy. That constraint severely limits what could occur. Any such behavior would be subtle and structureless. The core picture remains. The universe approaches a state where the difference between earlier and later loses meaning because nothing accumulates. Nothing distinguishes one moment from another. The universe becomes a continuous physical presence without narrative, not a story, not a process, not a cycle, simply a persistent condition. This is the quiet shape of heat-death.
Within this persistent condition, the idea of location also becomes less meaningful because location normally matters only when different places support different possibilities. Earlier, one region of space might contain a star, another might contain empty vacuum, another might contain a planet. These differences made spatial position significant. In the heat-death regime, every region is nearly the same. No place offers anything different from any other place. Coordinates still exist mathematically, but they no longer correspond to distinct physical situations. Space becomes homogeneous in the deepest practical sense. This homogeneity is not imposed. It emerges because nothing maintains heterogeneity. Earlier, heterogeneity was constantly produced by ongoing processes. Stars created heavy elements. Supernovae redistributed matter. Gravity clumped material. When these processes fade, nothing counteracts the natural smoothing of distributions. The universe becomes smooth because smoothing has no opponent. This also affects the meaning of distance. Distance is normally a measure of separation between things. When there are no distinguishable things, distance becomes a purely abstract parameter. One can assign numbers to coordinates, but nothing occupies those coordinates in a way that matters. The universe becomes geometry without geography. Another implication concerns isolation. Earlier, objects could be isolated from one another, but they were still embedded in networks of interaction. Light traveled. Gravity reached across space. In the far future, isolation becomes extreme. Interactions become so rare that almost nothing influences anything else. This extreme isolation reinforces uniformity. Even if two regions are separated by immense distances, they are physically equivalent. They contain the same kinds of particles at the same kinds of energies. Nothing distinguishes here from there. This again points toward a universe that has lost internal reference points. Reference points require landmarks. Landmarks require structure. Without structure, reference collapses. This loss of reference extends to all descriptive axes. Space loses landmarks. Time loses markers. Identity loses persistence. History loses records. What remains is a bare physical substrate evolving only in trivial ways. This substrate does not organize itself into higher-order forms. It does not self-describe. It does not self-differentiate. It simply continues. This continuation is not purposeful. It is not avoidable. It is what remains when nothing else can happen. Heat death is therefore best understood as a condition of maximal neutrality. No bias toward building, no bias toward collapsing, no bias toward change. Only the minimal motion allowed by physical law, spread evenly across everything that exists. At this stage, even the notion of an environment becomes unclear, because an environment is normally defined as the surroundings relative to a system. When no systems exist, there are no surroundings. Everything is just everything. Earlier, one could speak of objects embedded within space. Later, there are no objects to embed. There is only space filled with uniform physical content. This removes the distinction between container and contained. The universe is no longer a stage with actors. It is only the stage, and even the idea of a stage becomes unnecessary because nothing is being presented. This highlights how deeply relational many concepts are. They make sense only when multiple distinct entities coexist. When distinction collapses, relation collapses. Without relation, many concepts evaporate, not because they were wrong, but because their domain of application has vanished. Another subtle implication concerns explanation by origin. Earlier, one could ask where something came from. A star came from a gas cloud. A gas cloud came from primordial matter. A planet came from a disk. These questions presuppose that things have histories. In the heat-death regime, nothing has a meaningful history. Things do not persist long enough to have one. Configurations appear and disappear without lineage. The concept of ancestry loses meaning. Without ancestry, narratives of origin disappear. The universe still had a past, but nothing in the present refers to it. The past becomes physically disconnected from the present, not by breaking causality, but by eliminating memory. This again emphasizes that forgetting is not an act, it is a structural outcome. When nothing stores information, nothing remembers. The universe does not choose to forget, it simply lacks the capacity to remember. This condition also reframes the idea of permanence. Permanence is often imagined as lasting forever. In physics, permanence usually means lasting much longer than relevant timescales. In the heat-death regime, nothing lasts in an organized way, but the underlying physical substrate persists. This is a deeper kind of permanence, not permanence of form, but permanence of existence. Forms dissolve, existence continues. This distinction clarifies why heat death is not annihilation. Nothing is annihilated. Forms fade. The substrate remains. The universe becomes form-poor but existence-rich. Yet richness here does not mean variety. It means ubiquity. Everything is everywhere in the same way. This is not fullness in a qualitative sense. It is fullness in a uniform sense. The universe is full of itself, evenly, quietly and without differentiation.
With differentiation absent, the boundary between what counts as a state and what counts as a process becomes blurred. Because a state is normally understood as something that persists, while a process is something that unfolds. In the heat-death regime, nothing persists in a structured way, and nothing unfolds in a cumulative way. What exists is a continuous stream of microscopic fluctuations that do not build toward anything. These fluctuations are not steps in a process. They are not phases of a transformation. They are simply momentary configurations. One configuration replaces another, but the replacement has no direction. This means that describing the universe as being in a particular state is already a simplification. It is more accurate to say that the universe occupies a narrow family of similar states. From a macroscopic perspective, all of these states are indistinguishable. From a microscopic perspective, they differ in trivial ways. This reinforces the idea that heat death is not a frozen snapshot. It is a narrow band of ongoing, low-level activity. Another implication concerns possibility over extremely long durations. Sometimes it is suggested that given enough time, anything that is possible will eventually happen. This idea only holds when systems can explore their full range of configurations. In the heat-death regime, the system cannot explore that range because moving into highly ordered configurations requires coordinated motion across vast numbers of particles. Such coordination cannot arise spontaneously in a context without gradients or feedback. The universe is trapped not by walls but by probability. Almost all accessible microstates correspond to uniformity. Almost none correspond to complexity. The universe continually samples the accessible microstates. It almost never samples the inaccessible ones. This is what makes heat death effectively permanent, not absolutely permanent in a metaphysical sense, but permanent in any practical physical sense. Another subtle point concerns the role of observers in defining reality. Earlier, observers were physical systems that processed information and formed models. Their existence depended on complexity. In the heat-death regime, no observers exist. This does not mean that reality disappears. It means that reality no longer contains systems that construct representations. The universe still evolves according to its rules. It simply does so without internal description. All description exists only in theoretical frameworks developed earlier during the complex era. These frameworks describe a future that contains no describers. This asymmetry is unavoidable. Physics can describe states that contain no physicists. This does not create a paradox. It reflects the fact that description is external to what is being described. The universe does not need to be observed to exist. It does not need to be interpreted to behave. It simply follows its dynamics. Heat death is one of the long-term consequences of those dynamics. It is not a conclusion reached by the universe. It is a conclusion reached by models. The universe itself does not conclude anything. It simply continues in its simplest mode.
At this point in the conceptual flow, it becomes useful to notice that many familiar oppositions, such as full versus empty, active versus inactive, and moving versus still, lose their sharpness. The heat-death universe is not empty because physical content remains. It is not full in any structured sense because nothing forms. It is not active in a macroscopic sense because nothing develops.
it is not truly still because microscopic motion continues. These oppositions depend on intermediate regimes where contrasts are strong. In extreme uniformity, contrasts fade and oppositions collapse into softer distinctions. This suggests that many of the categories humans rely on are tuned to a narrow band of physical conditions. Outside that band, they become approximate at best. The heat-death regime lies far outside the band of conditions in which human concepts evolved. This is why intuitive language struggles to capture it. Another implication concerns change as a measurable quantity. Earlier, one could measure rates of change. Stars aged, radioactive elements decayed, systems evolved. In the far future, rates of macroscopic change approach zero. This does not mean that rates become exactly zero. It means that they fall below any scale that could support structure. Measurement itself becomes impossible because measurement requires instruments, and instruments require stable structure. Without structure, there are no measuring devices. This again emphasizes that heat death is not a state that can be observed from within. It is only describable from the outside in theory. Another subtle consequence concerns causality across large scales. Earlier, one could trace long causal chains. A supernova triggers star formation. A star produces heavy elements. Heavy elements form planets. In the far future, causal chains are extremely short. Interactions do not propagate into networks. They end almost immediately. This does not break causality. It trivializes it. Cause still leads to effect. Effect does not lead to further effects in any extended way. The universe becomes causally shallow. This shallowness is another expression of structural flatness. Where there are no layers, there is no depth. The universe becomes a single-layer system. Everything exists on the same level of description. There is no higher-order organization. There is no lower-order organization beyond the fundamental. This single-layer nature contributes to the sense in which nothing meaningful happens. Meaningful here refers to the production of durable differences. Without durable differences, nothing accumulates. Without accumulation, there is no story. The universe becomes storyless, not because stories are forbidden, but because the physical prerequisites for stories are gone. What remains is an endless continuation of minimal physical existence. In this regime of near sameness, the distinction between possibility and impossibility becomes mostly irrelevant, because while many configurations may still be possible in principle, almost none are reachable in practice. Reachability depends on pathways. Pathways depend on gradients. Gradients no longer exist. This means that the universe is not constrained by strict prohibitions, but by the absence of means. Nothing forbids a complex structure from existing. There is simply no process capable of producing or sustaining one. This absence of means is more fundamental than any rule. It explains why the future universe is simple without requiring additional laws. Simplicity emerges because construction requires resources, and resources are no longer available in usable form. Earlier, stars acted as engines that concentrated energy. Later, black holes acted as long-term reservoirs. Eventually, even these reservoirs fade. When all engines stop, no new engines can be built. the universe enters an engineless state. This concept helps clarify the difference between potential energy and accessible energy. Potential energy can exist as a number in an equation. Accessible energy is energy that can be converted into organized change. Heat death occurs when accessible energy effectively reaches zero, even though total energy remains. This distinction is central. The universe is not empty of energy, it is empty of usable energy. Another implication concerns causation. Causation is meaningful when causes reliably lead to effects that persist or propagate. In a high-entropy universe, causes still produce effects, but effects do not lead to further effects in extended chains. Causation becomes shallow. Events have no depth. A shallow causal world is one where nothing builds upon anything else. This again ties back to the absence of structure. Structure is what allows causes to echo forward. Without structure, causation collapses into isolated interactions. This does not violate physical law. It reflects a change in context. The same laws operate, but the environment no longer supports complex outcomes. The universe becomes a place where laws are expressed only in their simplest consequences. Over time, this simplicity becomes all that exists, not because something removed complexity, but because nothing sustains it. The disappearance of complexity is therefore passive. It happens by default. This passivity is one of the most striking features of heat death. There is no cosmic force pushing toward simplicity. There is only the absence of forces that push toward organization. Organization requires continuous effort. Simplicity does not. When effort becomes impossible, simplicity dominates. This framing removes any dramatic tone from the scenario. Heat death is not a disaster. It is not a collapse. It is the quiet outcome of a universe that has gradually spent its ability to differentiate itself. The universe does not mourn this state. It does not recognize it. It simply exists within it. From a physical standpoint, nothing is wrong. The universe is behaving exactly as expected. From a conceptual standpoint, the universe has reached the simplest expression of its existence. As the universe remains in this uniform persistence, the distinction between existence as presence and existence as process becomes increasingly important. Earlier, existence was strongly associated with ongoing activity. To exist meant to participate in processes. Stars burned, atoms bonded, organisms metabolized. In the heat-death regime, existence is no longer process-oriented. It is presence-oriented. Things exist in the minimal sense that physical quantities have values, not in the richer sense that those values participate in organized change. This reveals that process-based existence is a special case, not the default. The default mode of existence, at least for large closed systems, appears to be static presence with trivial internal motion. Another implication concerns expectation. Humans naturally expect continuity of change. This expectation is shaped by living in a gradient-rich environment. It is not a universal principle. The universe does not promise novelty. It does not guarantee transformation. Change occurs only when conditions allow it. When conditions do not allow it, change fades. This does not violate any rule, it fulfills them. Another subtle point concerns description by equations. The equations of physics continue to apply in the heat-death regime. They still specify how fields and particles behave. But the solutions to these equations become simple. There are no complex boundary conditions. There are no interesting initial conditions. Everything is close to uniform. The mathematics becomes trivial in outcome, even if the equations themselves remain the same. This again shows that richness of behavior depends more on conditions than on laws. Laws constrain, conditions express. When conditions are simple, expressions are simple. Another implication concerns irreversibility. Earlier, irreversibility was associated with visible change. A broken cup does not reassemble. A burned log does not unburn. In the heat-death regime, irreversibility becomes invisible because nothing visibly changes. Yet the underlying irreversibility that drove the universe toward this state has already done its work. The universe is deep in the most probable region of its configuration space. There is no path back toward low entropy that is physically accessible. This is not because backward paths are illegal. It is because they are so improbable that they never occur. This probabilistic irreversibility is sufficient to lock the universe into simplicity. Another implication concerns finality. Heat death is often described as the final state of the universe. A more precise description is that it is a terminal regime. A regime is a mode of behavior. The universe enters a mode where nothing accumulates. It may remain in this mode indefinitely. There is no evidence within current physics for a transition out of this mode. The universe does not cycle back. It does not reboot. It does not spontaneously restart complexity. It simply persists. This persistence is not dramatic. It is quiet. It is uneventful. It is minimal. And in that minimal persistence, the long arc of cosmic relaxation reaches its natural limit.
In this terminal regime, the idea of accumulation becomes essentially meaningless, because accumulation requires that changes stack on top of one another, and stacking requires persistence. Earlier, matter accumulated into stars, energy accumulated in gradients, information accumulated in memories. In the heat-death regime, nothing stacks. A fluctuation appears, it disappears, nothing builds upon it. There is no layering, there is no sediment of events. Each moment stands alone, even though moments themselves are not distinguishable. This absence of stacking is another way of describing the absence of history. History is not simply a sequence of events. It is a sequence where earlier events constrain later ones in lasting ways. Without constraint, sequences dissolve into unrelated occurrences. The universe still has a parameter called time. It does not have history in any functional sense. Another implication concerns the idea of cause having consequences. Earlier, a cause could ripple outward. A supernova could reshape a region of space. A chemical reaction could alter an environment. In the far future, a cause produces only an immediate effect. The effect does not propagate. It does not reshape anything. Causation becomes local and shallow.
This does not make the universe acausal. It makes it consequence poor. Events happen. They simply do not matter to anything else. This concept of mattering is physical, not emotional. Matter means to influence future states. In the heat-death regime, influence does not extend. The universe becomes a collection of self-contained micro-events. Another subtle point concerns direction. Earlier, many processes had a clear direction. Things cooled, stars aged, structures decayed. In the terminal regime, direction disappears. There is no overall trend left. The trend toward equilibrium has already been realized. After that, nothing trends. There is no forward towards something. There is only continuation within sameness. This does not contradict the arrow of time. The arrow still exists as a statistical statement, but its expression has reached its asymptote. The arrow no longer produces visible change. Another implication concerns emergence. Emergence refers to higher-level patterns arising from lower-level interactions. Emergence requires feedback, non-linearity, and energy flow. Without energy flow, emergence stops. The universe becomes non-emergent. Everything that exists is already at the lowest relevant level. Nothing higher arises. This again reinforces that heat death is not destruction of higher levels. It is the disappearance of the conditions that allow higher levels to exist. The universe does not tear structures apart violently. It simply stops holding them together. Over long durations, they fade. What remains is a simple, quiet physical substrate, continuing without layering, without accumulation, and without development. In this quiet substrate, even the concept of transition becomes questionable, because a transition implies movement from one distinct condition to another, and in the heat-death regime, all accessible conditions are nearly identical. The universe still changes microscopically, but these changes do not move it into qualitatively different macroscopic states. There are no phases, no epochs, no chapters. Earlier in cosmic history, one could meaningfully divide time into eras. There was a time of star formation, a time of galaxy assembly, a time when heavy elements became common. In the far future, such divisions lose meaning. All times resemble one another. This sameness across time mirrors the sameness across space. The universe becomes homogeneous in both dimensions. Another implication concerns the idea of boundaries between inside and outside. Earlier, systems had interiors. A star had an inside and an outside. A cell had a membrane. A brain had an internal state distinct from its environment. In the heat-death regime, no such systems exist. Without systems, there are no insides. Everything is outside. Or, more precisely, everything is neither inside nor outside. The distinction collapses. This again reflects the disappearance of organization. Boundaries are features of organized systems. When organization disappears, boundaries disappear. Another subtle point concerns energy levels. Earlier, energy could be concentrated in specific places. A star was a high-energy object embedded in lower-energy space. In the far future, Energy is spread so thinly that no place qualifies as high energy relative to any other. This does not mean that energy density becomes exactly the same everywhere. It means that any differences are too small to drive structure. The universe reaches a practical uniformity. Practical uniformity is sufficient to eliminate complexity. Absolute uniformity is unnecessary. Another implication concerns interpretation. Humans often interpret the universe through stories. Even scientific explanations are sometimes framed as narratives. Heat death resists narrative framing. There is no climax, no resolution, no twist. There is only a long settling into simplicity. Any attempt to dramatize this process introduces human projection. The physical reality is plain. A large closed system relaxes. When relaxation is complete, nothing interesting happens. This plainness is not a defect of the theory. It is a feature. It reflects the minimalism of statistical behavior. The universe does not behave like a story. It behaves like a system. Heat death is what a system does when left alone long enough.
At this point, the cumulative picture of the far future universe can be understood as a world without reference points. Reference points are anchors that allow comparison. A mountain is tall relative to a plane. A clock is fast relative to another clock. A region is hot relative to a cooler region. In the heat death regime, relative differences are negligible. Without relative differences, nothing can serve as a reference. Comparison collapses. Without comparison, many descriptive statements lose content. Saying that something is large, small, fast, slow, bright, dim, old, or young becomes meaningless because there is nothing to compare it to. This does not mean that physical quantities cease to exist. It means that relational meaning disappears. This again emphasizes how much of reality, as experienced, is relational rather than absolute. Another implication concerns scale of explanation. Earlier, one could explain behavior at different scales. Microscopic physics explained atoms. Atomic physics explained chemistry. Chemistry explained biology. Biology explained cognition. These layered explanations depended on the existence of stable intermediate levels. In the heat death regime, intermediate levels vanish. Only the most fundamental level remains relevant. Explanation collapses downward. Everything is described at the same basic level. This does not make understanding deeper. It makes understanding flatter. There are fewer levels to connect. Another subtle point concerns symmetry between past and future. Early in this series, it was noted that the laws of physics are mostly time-symmetric, yet the universe shows a clear arrow of time. In the heat death regime, this asymmetry becomes invisible. The universe looks the same forward and backward over small intervals because nothing changes in a macroscopic sense. This does not mean that the arrow of time has reversed. It means that the arrow has reached a region where its effects are no longer visible. The arrow still exists as a statistical statement about probabilities. It simply no longer produces noticeable differences. Another implication concerns necessity. Earlier, many processes felt necessary. Stars must burn, atoms must combine, systems must decay. In the far future, nothing feels necessary because nothing significant happens. The universe does not have to do anything, it simply is. This is not because the universe has achieved a goal. It is because it has exhausted the conditions that force change. Forced change requires imbalance. Imbalance is gone. What remains is optional motion.
motion without consequence. The universe continues as a minimal physical presence, not because it is compelled to move forward, but because nothing compels it to do otherwise. This is the quiet neutrality of heat death.
In this neutral persistence, the distinction between potential and actual also becomes less meaningful, because potential usually refers to something that could be realized under the right conditions. In the heat death regime, there are no right conditions. There is no environment that can unlock hidden possibilities. One might say that the universe still contains countless potentials in a purely abstract sense, but abstraction alone does not produce reality. Reality requires pathways. Pathways require gradients. Gradients are absent. Potential without pathway is indistinguishable from impossibility. This reframes how possibility should be understood in extreme contexts. Something can be logically conceivable, yet physically unreachable. Heat death is the regime where almost all complex logical possibilities become physically unreachable. Another implication concerns expectation of novelty. Humans often expect that the future contains surprises. This expectation is again shaped by living inside a gradient-rich era. It is not a universal rule. The far future contains almost no surprises, because surprise requires deviation from expectation, and expectation becomes trivial. The expected state is uniformity. The observed state is uniformity. There is nothing to be surprised by. Another subtle point concerns reductionism. In the complex era, reductionism and emergence coexist. One can explain systems in terms of parts, but new patterns arise at higher levels. In the heat death regime, reductionism dominates completely, not because it is philosophically superior, but because nothing emerges. Everything that exists is already at the lowest relevant level. This does not vindicate any philosophical position. It reflects a physical condition. Another implication concerns language itself. Language evolved to describe structured environments. Nouns label objects. Verbs label actions. Adjectives label properties. In the heat death regime, objects are absent. Actions are trivial. Properties are uniform. Language loses traction. There is nothing to point to. There is nothing to distinguish. Any sentence applies everywhere or nowhere. This again emphasizes that description is contingent on structure. When structure disappears, description becomes redundant. The universe continues, but it no longer supports description from within. It exists as an undifferentiated physical presence, changing microscopically, unchanging macroscopically, indefinitely. As the universe remains in this undifferentiated condition, it becomes increasingly clear that what once felt like motion through time has transformed into mere succession without significance. Earlier, succession meant progress from one distinguishable state to another. Now, succession is simply one nearly identical microstate following another. There is still ordering. One configuration follows another, but ordering without distinction carries no experiential weight. This highlights a crucial separation between sequence and story. A story requires difference between moments. Sequence alone is not enough. The heat-death universe has sequence, it does not have story. Another implication concerns the disappearance of tension.
Tension arises when systems are out of balance. Tension drives change. It produces release. In the far future, there is no tension. Everything is balanced. Without tension, nothing drives toward anything else. This again reflects the exhaustion of gradients. Another subtle point concerns the role of chance versus necessity. Earlier, some events felt inevitable. Stars must burn through their fuel. Others felt contingent. A particular planet might or might not form. In the heat-death regime, nothing feels inevitable or contingent because nothing significant happens. The distinction collapses. The universe exists in a mode where events lack weight. They neither fulfill necessities nor explore possibilities in any meaningful sense. They simply occur and vanish. Another implication concerns the idea of directionality in explanation. Earlier, one could explain the present by referencing the past. The present contains traces of what came before. In the heat-death regime, the present contains no traces. Explanation by origin loses meaning. There is nothing in the present that encodes the past. The universe has a past, it does not remember it. This does not require erasure, it requires only the absence of storage. Storage requires structure. Structure is gone. The universe becomes amnesic in a physical sense, not forgetful as an action, but incapable of remembering. This incapacity is permanent because nothing can rebuild the structures that would be required for memory. The universe therefore persists in a condition without narrative, without reference, and without accumulation. It is not waiting, it is not ending, it is simply continuing in its simplest possible mode. At this stage, even the notion of an environment becomes unclear, because an environment is normally defined as the surroundings relative to a system. When no systems exist, there are no surroundings. Everything is just everything. Earlier, one could speak of objects embedded within space. Later, there are no objects to embed. There is only space filled with uniform physical content. This removes the distinction between container and contained. The universe is no longer a stage with actors. It is only the stage, and even the idea of a stage becomes unnecessary because nothing is being presented. This highlights how deeply relational many concepts are. They make sense only when multiple distinct entities coexist. When distinction collapses, relation collapses. Without relation, many concepts evaporate, not because they were wrong, but because their domain of application has vanished. Another subtle implication concerns explanation by origin. Earlier, one could ask where something came from. A star came from a gas cloud. A gas cloud came from primordial matter. A planet came from a disk. These questions presuppose that things have histories. In the heat-death regime, nothing has a meaningful history. Things do not persist long enough to have one. Configurations appear and disappear without lineage. The concept of ancestry loses meaning. Without ancestry, narratives of origin disappear. The universe still had a past, but nothing in the present refers to it. The past becomes physically disconnected from the present, not by breaking causality, but by eliminating memory. This again emphasizes that forgetting is not an act, it is a structural outcome. When nothing stores information, nothing remembers. The universe does not choose to forget, it simply lacks the capacity to remember. This condition also reframes the idea of permanence. Permanence is often imagined as lasting forever. In physics, permanence usually means lasting much longer than relevant timescales. In the heat-death regime, nothing lasts in an organized way, but the underlying physical substrate persists. This is a deeper kind of permanence, not permanence of form, but permanence of existence. Forms dissolve, existence continues. This distinction clarifies why heat death is not annihilation. Nothing is annihilated. Forms fade. The substrate remains. The universe becomes form-poor but existence-rich. Yet richness here does not mean variety. It means ubiquity. Everything is everywhere in the same way. This is not fullness in a qualitative sense. It is fullness in a uniform sense. The universe is full of itself, evenly, quietly, and without differentiation.
In this bare physical self, even the notion of remaining becomes slightly misleading, because remaining implies that something else has gone away. Yet, from the universe's own perspective, nothing has been subtracted. Forms faded because they could no longer be supported, not because they were removed. The underlying physical content has been continuous throughout. This highlights that the universe does not lose substance over time. It loses organization. Organization is conditional. Substance is not, at least within current physical understanding. Another implication concerns decay. Earlier, decay referred to the transformation of organized systems into less organized ones. In the heat-death regime, decay no longer occurs because nothing organized exists to decay. The era of decay has already passed. What remains is post-decay existence. This is an important distinction. Heat death is not an ongoing decay process. It is the condition reached after decay has effectively completed. Another subtle point concerns the meaning of after. After usually implies a difference between before and after. In the heat death regime, after and before are almost indistinguishable. This again shows that language built for change struggles to describe a state of near non-change. Another implication concerns the notion of completeness. Heat death is sometimes described as the universe reaching completion. This language is misleading because completion suggests fulfillment of a purpose. There is no purpose. A better description is saturation. All processes that can occur have occurred. All gradients that can be flattened have been flattened. Saturation does not imply success. It implies exhaustion of possibilities. Another subtle point concerns continuity of physical law. The laws have not changed. The universe has not entered a new rule set. Everything that happens in the heat death regime happens under the same rules that govern star formation and nuclear fusion. The difference is entirely in conditions. This reinforces that dramatic cosmic endings are not required by physics. The most extreme future emerges from ordinary rules applied for a very long time. The universe does not need to break its laws to become simple. It becomes simple by following them. In this sense, heat death is the most conservative possible ending. Nothing extraordinary happens. Everything gradually becomes ordinary. As everything becomes ordinary in this deepest possible sense, even the word ordinary begins to lose meaning, because ordinary only makes sense when contrasted with extraordinary, and no such contrast remains. The universe no longer contains a spectrum of conditions. It contains a narrow band. When all conditions are similar, nothing qualifies as special, but nothing qualifies as typical either. Typicality itself depends on variation. Without variation, statistics lose much of their intuitive role. The universe still occupies the most probable region of its configuration space, but probability no longer expresses anything interesting because there are no competing macroscopic alternatives. This marks a quiet endpoint for statistical behavior as something that produces visible consequences. Statistics still applies, it simply no longer produces structure. Another implication concerns explanation by dynamics. Earlier, one could say that something happens because forces push it to happen. Gravity pulls matter together. Pressure pushes outward. Radiation carries energy away. In the heat-death regime, forces still exist, but they no longer generate large-scale motion. The balance between forces is so uniform that nothing accelerates in any meaningful way. Dynamics become trivial. Equations still govern motion, but motion does not organize. This suggests that dynamics without structure are effectively invisible at macroscopic scales. The universe becomes dynamically silent, not because nothing moves, but because nothing moves in a way that matters. Another subtle point concerns resilience. Earlier, some systems were resilient. They could recover after disturbance. A biological organism could heal, an ecosystem could regrow. Resilience requires stored energy and internal organization. In the heat-death regime, nothing is resilient because nothing is organized enough to be disturbed in a meaningful sense. Disturbance itself loses meaning. There is no baseline structure to disturb. Everything is already in its simplest configuration. Another implication concerns the idea of minimum. Heat death is often described as a minimum energy state, but this can be misleading. It is not that energy is minimal, it is that usable energy is minimal. The universe has not lost its energy, it has lost its gradients. This distinction continues to be central. It prevents the false image of a drained universe. The universe is not drained, it is leveled. Another subtle point concerns the idea of waiting. Sometimes heat death is imagined as the universe waiting forever. Waiting implies expectation. Expectation implies the possibility of something else. In the heat death regime, nothing else is physically accessible. Therefore, waiting is not an appropriate description. The universe is not waiting, it is simply persisting. Persistence without anticipation. Persistence without direction. Persistence without destination. This persistence is not a state of suspense, it is a state of completion in the sense of saturation, not in the sense of fulfillment. The universe has fully expressed what it can express under its conditions. What remains is the minimal expression of physical existence. In this minimal expression of physical existence, the distinction between complexity as a feature and complexity as an exception becomes clearer. Earlier in cosmic history, complexity felt abundant. Stars filled galaxies. Chemistry filled space with diverse molecules. Life in some regions added further layers of organization. From that local perspective, complexity appeared natural. From the long-term perspective, complexity is rare. It arises only during a narrow window when conditions briefly allow it. Heat death reveals this rarity by showing what existence looks like when those conditions no longer hold. The universe does not naturally tend toward complexity. It naturally tends toward equilibrium. Complexity appears only as a transient deviation from that tendency. This does not diminish complexity, it contextualizes it. Another implication concerns the idea of effort. Earlier,
Maintaining structure required continuous effort in a physical sense. Stars required nuclear fusion. Organisms required metabolism. Even inert structures required energy barriers to remain intact. In the heat-death regime, no effort is possible. But also, no effort is needed because nothing attempts to remain organized. The universe is not maintaining anything. It is not sustaining forms. It is simply existing. This reveals that effort is a property of non-equilibrium systems. When equilibrium dominates, effort disappears. Another subtle point concerns inevitability. It is sometimes said that heat death is inevitable. A more precise statement is that heat death is the overwhelmingly probable outcome given current understanding of physical law and cosmology. This distinction matters because inevitability suggests certainty rooted in necessity, while probability reflects statistical dominance. The universe behaves statistically. Over immense timescales, statistical dominance becomes effectively certain. This is why heat death is treated as the expected future, even though absolute certainty is not claimed. Another implication concerns directionlessness. Earlier, the universe exhibited many directed processes. Expansion proceeded, stars evolved, structures assembled and disassembled. In the heat-death regime, direction disappears, not because time has stopped, but because nothing has a preferred path. All accessible states are equivalent. The universe does not move toward anything. It does not move away from anything. It simply occupies. This occupancy is not a choice. It is not an action. It is a condition. Another subtle point concerns the difference between absence of meaning and presence of neutrality. Heat death is often interpreted emotionally as meaningless. From a physical perspective, it is neutral. Meaning is not something physics assigns or removes. Meaning arises within certain physical systems. When those systems cannot exist, meaning does not exist either. This is not a negative outcome. It is simply outside the domain of physical description. The universe does not require meaning to function. It does not require narrative. It does not require interpretation. It only requires that physical quantities evolve according to their relations. Heat death is one of the long-term expressions of that evolution. It is quiet, it is simple, it is stable, and it is not dramatic.
As this quiet stability persists, the contrast between earlier cosmic eras and the terminal regime becomes increasingly abstract because nothing within the terminal regime points back to what came before. The difference exists only in theoretical reconstruction. Physics can infer that the universe once contained stars, galaxies, and complex structures. The heat-death universe itself contains no evidence of this history. It is not a ruin, it is not a remnant, it is not an aftermath in a visual sense, it is simply a uniform physical condition. This highlights that history is not an intrinsic property of a system. History exists only when records exist. Records require stable structures. Without stable structures, history vanishes. Another implication concerns the idea of loss. From a human perspective, one might describe the disappearance of complexity as loss. From a physical perspective, nothing is lost. Energy is conserved. Physical laws are unchanged. Only organization disappears. Organization is not conserved. There is no conservation law for structure. Structure is contingent. It arises and fades. Heat death is the regime where fading has completed. Another subtle point concerns quietness.
Quietness is often associated with absence of sound. In this context, quietness refers to absence of large-scale activity. There is no cosmic silence that could be heard because hearing requires ears, and ears require organisms, and organisms require complexity. Quietness here is a conceptual descriptor. It points to lack of macroscopic dynamism. Another implication concerns the role of extreme timescales. Heat death occurs over timescales so long that ordinary numbers lose meaning. Yet the exact duration is not important. What matters is the direction of change. Even if the universe lasts forever, the trend toward equilibrium remains. Whether equilibrium is reached in finite or infinite time does not change the conceptual picture. The universe asymptotically approaches a regime where nothing significant happens. Another subtle point concerns the possibility of unknown physics. Future discoveries could modify details. They could introduce new particles, new interactions, or new cosmological behavior. However, as long as the universe remains a closed system without external energy input, any such modifications would still be constrained by entropy. They might alter the path, they would not eliminate the tendency toward equilibrium. Heat death is therefore robust across many possible future theories. It is not tied to a specific model. It is tied to a general statistical principle. The universe, left alone, relaxes. When relaxation has gone as far as it can go, what remains is a simple, uniform, uneventful physical presence. At this stage, the conceptual space around heat death becomes extremely narrow because most distinctions have already dissolved. What remains to consider is not what happens, but what it means for nothing to happen. Earlier, nothing happening might have been interpreted as a pause between events. In the terminal regime, nothing happening is not a pause. It is the dominant mode. There are no events waiting to occur. There is no latent activity preparing to emerge. There is only continuous minimal fluctuation without consequence. This clarifies that inactivity here is not suppression. It is not restraint. It is not tension held in check. It is simply absence of conditions for activity. Another implication concerns the idea of background expectation. Humans often imagine that reality should do something, that something should be going on. Heat death challenges this intuition. It presents a model where reality does not owe activity to anything. Activity appears only when conditions allow it. When conditions do not allow it, reality is quiet. This quietness is not a failure of the universe. It is not an error state. It is a natural outcome of statistical behavior. Another subtle point concerns the idea of fundamental mystery. Earlier, complexity and emergence might have been seen as mysterious. In the heat death regime, mystery itself becomes irrelevant. Mystery presupposes unanswered questions about structure or behavior. When behavior is trivial and structure absent, there is nothing left to be mysterious about in a practical sense. This does not mean that ultimate questions about why the universe exists vanish. It means that such questions no longer connect to any observable phenomena. They become purely abstract. The universe continues regardless of whether those questions are posed. Another implication concerns the role of perspective. From within a complex era, heat death appears distant and extreme. From the standpoint of physical law, heat death is ordinary. It is what large, closed systems tend to do. The complex era is the anomaly. This inversion of intuition is one of the deepest lessons of thermodynamics. Order is special. Disorder is typical. Heat death is typical. Another subtle point concerns the idea of completion without closure. Heat death completes a process. It does not close a story. There is no final chapter. There is no last page. There is no last scene. There is only continuation in minimal form. The universe does not stop. It does not end. It does not vanish. It simply persists as a uniform physical presence, without differentiation, without accumulation, and without internal landmarks.
As the universe persists in this uniform condition, the final remaining distinction to soften is the difference between beginning and ending. Earlier, beginnings were associated with emergence of structure. Endings were associated with collapse or disappearance of structure. In the heat-death regime, neither description applies. Nothing new begins, nothing definitively ends. Structures have already faded. What exists now is neither a birth nor a death, but a continuous minimal presence. This suggests that the language of beginnings and endings is appropriate only within the complex interval of cosmic history. Outside that interval, the universe is better described as simply existing in different modes. The early universe existed in a highly constrained, concentrated mode. The middle universe existed in a dynamically complex mode. The late universe exists in a highly diffused, saturated mode. None of these modes represent absolute creation or absolute termination. They represent different distributions of the same underlying physical content. Another implication concerns the idea of total exhaustion. Heat death is sometimes imagined as everything being used up. A more precise description is that everything has been redistributed. Energy has not vanished, matter has not vanished, space has not vanished. What has vanished is asymmetry. Asymmetry is what allowed change to appear directional. When asymmetry disappears, direction disappears. This absence of direction is what gives the impression of finality. Yet physically, nothing has concluded. There is no cosmic punctuation mark. There is only an extended region of near sameness. Another subtle point concerns continuity of existence across all phases. The same physical substrate underlies the early universe, the complex universe, and the heat-death universe. There is no point where the substrate switches off. This continuity means that heat death is not an external fate imposed upon the universe. It is an internal transformation of how the universe expresses itself. Earlier, expression was rich. Later, expression is minimal. The universe does not cease expressing. It expresses less. Another implication concerns the absence of any privileged moment. No moment in the heat-death regime is special. No moment marks a threshold. No moment can be identified as the moment heat-death arrived. The transition is gradual and asymptotic. The universe slides into simplicity so smoothly that there is no line to cross. This reinforces the idea that heat death is not a destination reached at a specific time. It is a condition that increasingly dominates. By the time it dominates almost completely, nothing remains that could register the change. The universe has quietly become what it will continue to be. At the furthest edge of this conceptual path, what remains is the recognition that heat death describes the simplest, stable way a universe can exist while still obeying physical law. It is not a dramatic finale. It is not a catastrophic disappearance.
It is not a collapse into nothingness. It is the quiet persistence of physical existence without the capacity for complexity. The universe still contains energy. It still contains particles and fields. It still evolves microscopically, but it no longer supports structure, memory, accumulation, or experience. Everything that depends on differentiation has quietly faded. What remains is an even distribution of physical quantities across vast space, changing only in trivial ways. This condition does not resolve the deepest philosophical question of why there is something rather than nothing. It does not attempt to. It simply describes what happens to something when left alone under known physical tendencies for extremely long periods. The universe does not seek this condition. It does not avoid it. It drifts into it because almost all physical paths lead there. Once there, it has no internal means to leave. The long arc from concentrated beginnings, through a brief era of complexity, into diffuse simplicity, is not a story of rise and fall. It is a story of relaxation. A system that began far from equilibrium gradually relaxes toward equilibrium. Everything that appears along the way is a transient pattern inside that relaxation. Heat death is the name given to the regime where relaxation has effectively completed. Beyond that point, nothing new accumulates, nothing develops, nothing differentiates. The universe continues as a minimal physical presence, not empty, not dead, not alive, simply present.
As we come to the end of this session, there's nothing you need to take with you. No ideas to hold on to, no thoughts to finish. The words can fade, just like the day slowly does. If you found this space calming, you can leave a like or subscribe to the channel. It quietly supports more moments like this. For now, let everything settle. You don't need to listen closely anymore. The sound can stay, even as attention drifts away. Rest easy, and let time continue gently